Okay. Yeah. Yeah. I have some.
¿Tienes algún problema con...?
Sí, por la pantalla, sí.
Nosotros
es que me
lo
he ido
vemos bien, ¿eh?
me he ido a la última línea. Y,
You use arrows on your keyboard.
yes.
Flechas arriba y abajo del teclado. Igual te va bien.
Sí, bien,
Sí.
gracias.
Flechas. Arrows.
Okay.
Okay.
Now it's right. Now it's okay. Okay. First, I'm sorry to put 6th of May instead of 6th of April, because now it's April. It's not May. Okay. Today, first, my best greetings and wishes for all community of dynamical systems, concentrated very big start of dynamical system on this conference, on this workshop. Today I'm going to talk of some things concerning homoclinic trajectories on discrete dynamical system of dimension 1 and 2. On dimension n is several things are similar, but not all, of course. Okay. Now I go to start with first new definitions. In a dynamical system, first the dynamical system will be I with this compact real interval and a continuous map. What is a homoclinic trajectory? It's not a non-periodic trajectory whose alpha limit and omega limit set coincide, and both are a cycle. With a cycle, as usual, I mean a periodic trajectory. A point is called homoclinic if it belongs at least one homoclinic trajectory, at least one of them. Homoclinic trajectories are relevant, I think, because when they are present, the dynamical system has trajectories very complicated. Now it's necessary for us to understand something of this, because in this case you take the opportunity to know more and more of the behavior of all rest of trajectories. You know that the idea of the definition of homoclinic point and homoclinic trajectories were introduced by Poincaré at the end of the 19th century to describe a point belonging simultaneously to both stable and unstable manifolds of hyperbolic periodic points, always in plane diffeomorphism. But when we are not in the diffeomorphism, we have to adapt the definitions. This is why Bloch, Koppel, and Fedorenko-Tcharkovsky introduced new definition, not new but adapted definition for homoclinic trajectories or homoclinic points. I have given this definition. The first, their alpha limit, and if it exists, and omega limits coincide and are a cycle. One important property of this is this equivalence. If one dynamical system, now we are in dimension one, a real compact interval and a continuum has a homoclinic trajectory, this is equivalent to the map has a cycle whose period is not a power of 2. This is a well-known result. We can find it in several papers by Bloch, from Bloch, the Bloch book, etc. Of course, Fedorenko and Tchaikovsky result on several papers. And interesting thing is also both conditions are equivalent to positive, to have positive topological entropy in the system. We can be more precise if we of homoclinic or trajectory, if a map has a cycle of period different of a power of 2, the system has a homoclinic trajectory, but more can be said. It is attracted by some cycle of period n for some m. The second interesting thing is we can describe a coexistence of homoclinic trajectories. This is a valuable following classification for this. We can say that the attraction to the cycle of period n can be of two different ways. In this sense, we say that a homoclinic trajectory attracted to a cycle of period n will be called an homoclinic or 2n homoclinic. In the first case, we are talking about that there is a point in the cycle to which the homoclinic trajectory approaches along only one side, by one side, when n goes to minus infinity. In the second case, when we call the homoclinic trajectory 2n, the attraction is made in a different way, mainly in two-sided way, alternating one side and the other. This coexistence can be stated in the following way. If a dynamical system has a p homoclinic trajectory, then it also has a p prime homoclinic trajectory for any p prime such that p, a row p prime, the word design, this is a row, denote one ordering. This classification, this organization was introduced by Fedorenko and Tchaikovsky in the 80s, and this is the following: 1 implies 3, 5, and so on. Then 2 multiplied by 1 imply 2 multiplied by 3, and so on. Then the same power of 2 multiplied by 1, 3, etc., and so on. This is an organization of natural numbers with some ordering. This ordering seems similar to Tchaikovsky's ordering on cycles, but in fact there is a little differences. For example, in this ordering, numbers 2 over k, for k positive or 0, are moved into a block consisting of all numbers which are product of 2 over k for one odd number, so that the number 2 over k is the strongest element of the block. So is the first, in fact, is the first element in the block containing the product of these 2 over k, 2 multiplied by odd numbers. In particular, the strongest of all organization, all ordering of this scheme is number 1. This is something similar to, or you can see concerning the Tchaikovsky or well-known ordering on cycles. But what I'm now going to deal is with one characteristic, but for real functions, not necessarily continuous. We can define this total variation of iterates with this formula. The supremum in all finite partition of one compact subinterval of I. Oh, sorry. Okay. If we consider all the partitions with this 0, x0 and so on, and these are the string or the interval, and more complicated cases, we can call these them ecotic cases, Devani, sensitive dependence, etc. The iterates of one real number display oscillation, oscillatory behavior, which is observed, can be observed graphically when we try to represent the different iteration, the iterates of one real map F. We have here this formula. This is the definition. We call this characteristic the total variation of the real map. When in case we will apply this definition to our case or dynamical system, we can have 4 cases of growth or total variation of iterates. First, the total variation we fix on I, for example, remains bounded or grows unbounded, but not exponentially with respect to the iteration, or the total variation grows exponentially, or even more in difficult thing to understand, the total variation grows unbounded on every compact subinterval of I. This is a more complicated situation. The third of this item, number 3, is what is connected with homoclinic trajectories. To this end, to this respect, we have two results stating this connection with a system or not of homoclinic trajectory. The first is if F is homoclinic, has a homoclinic trajectory, then the limit when n goes to infinity of the total variation over the closure of the periodic points of F of Fn is in plus infinity, where Pf denotes the periodic point of F. And second result, when F is piecewise monotone, then there are equivalent between the two conditions. and the variation of f on this side is exponentially with respect to n, but which means that this is this form, a constant, positive constant multiplied by exponential bn, big n, when these are positive constant. Okay, after this property, this equivalent two words concerning the two-dimensional dynamical system. See, if we try to do the same to export these to two-dynamical system, we have many important differences. First, we can use the same definition of homoclinic trajectory or homoclinic point done in the dynamical system of the interval. If we do this, they appear. There are some equivalences derived on the classification of triangular maps. We concentrate in this because it's well known, and this was impulses by Tchaikovsky and other people. A lot of work has been made. I am referring to capital F X Y as this one, as usual, where F, small f and small g, are continuous and the domains of definition. These some people, Forti, Paganoni, and Professor Vital constructed a family of triangular maps possessing periodic trajectories at all periods and such that no infinity omega limit set of f contains a periodic point. When you have a point with an infinity omega limit set containing a periodic point, this is a very complicated situation. But this was constructed by these authors in a family, depending on one parameter. When it seems that this would be the same in two dimensions, but it's not. Even in this case, in the triangular situation, we have a case, not only a case, a family of cases, but some example proving that even in this family, we could have homoclinic trajectory, which implies that at least one infinity omega limit set contains a periodic trajectory. This is different with the interval case. Finally, I'm going to comment a little, very briefly, an example constructed by myself and Jaroslav Schmidl of a map having possessing an homoclinic trajectory. I mean, triangular map. Is the base, the map in the base is this function. This is a 10th map without some cut at the end, at the top. Is immediately that f has a periodic trajectory of all periods, since has a periodic point or periodic trajectory of period 3. So it has periodic trajectory of all periods. In this case, for this map, it's not difficult to find an homoclinic trajectory to the fixed point 0. And this given is described by this formula. It's composed of the point 0 union with the sequence 3 over minus n. And since and in this case, f of 1 is 0, and then the image of this 3 over minus n minus 1 is 3 minus n. And now we complete, it's necessary to complete this this map. To this end, we use an intermediate situation with some using different type of continuous and so on. Finally, we are able to prove that in such case we have this gamma, capital gamma, composed of these points, 0 p is a real number, union of this, where yn is a sequence constructing a way that the limit of this sequence be p. In that case, we have this as a homoclinic trajectory, but this map is belonging to this class constructed by these authors. So we have a situation in which one of the map belonging to this family can be a homoclinic trajectory when all properties similar to the case of the interval. We have also, my last consideration, other two-dimensional system, not on the square and not on the familiar triangular map. But it's difficult to give explicit expression for homoclinic trajectory. In the first example, we studied the dense or such trajectory in one family, well known, the two delayed logistic equation or family of maps, depending on one parameter A. It's possible to find a special expression, concrete expression of these homoclinic trajectories in this case. Also, more complicated things like two-mode transformation written on this way, and so on, and other more situation in not in dimension 2, even in dimension n. Okay, this is all. Thank you for your attention, and I finish now.
Okay, Francisco.